Okay. Thanks. So thank you all for the techniques and also for this wonderful conference. And thanks, Nasser, for the presentation. So today I'm very happy to to have the opportunity to present our research on large momentum transfer atom optics. So in my talk, I will discuss how we have applied the floquet formalism together with quantum optimal control to develop very efficient atom optics and a large momentum transfer interferometer. So we have already had some context today about these large-scale atom interferometers. So in our group, we target to have a separation between the two arms of the interferometer of about greater than 10 centimeters. We want to be able to fit some controlled perturbation on single arm of the interferometer. So with that kind of separation, we can test eventually atom neutrality, and also we hope to make some new measurements of the gravitational constant big G. To achieve such a high separation, we need to have a large momentum transfer greater than 200 h-bar K. This is why we study that kind of atom optics. We have also heard about this the fact that in the community there are projects that explore the possibility to create new gravitational detectors based on interferometer with momentum transfer greater than 1000 h-bar K, and much more than 1000 h-bar K, if I have well understood today. So the most common solution for that is first to create a beam splitter with a superposition, a coherent superposition between 2 h-bar K, 0 plus 2 h-bar K, and then to have an acceleration of a single arm with either a sequence of pulses or an acceleration, a continuous acceleration in an optical lattice. So if we want to achieve that, we need a very high efficiency. Okay, since as we have a cumulative loss, if you add more and more pulses, you will have an exponential decay of the remaining atoms. And to give you an idea, if you want to keep, let's say, more than 60% of the atom in the acceleration in the interferometer, you need more an efficiency per h-bar K, which is more than 99.99% efficiency per h-bar K. In addition, you also need to have a very fast momentum transfer, as you want to fit all your pulses in a given time of flight, which is limited on Earth. So to achieve that, there are many various demonstrations that have demonstrated a momentum transfer higher than 100 h-bar K. So we hear today about the single photon techniques, and maybe Jan will speak about it, or will discuss that on Thursday. And today I will focus on another very efficient solution, which use manipulation of atom in an optical lattice. So you can use a sequence of Bragg pulse or continuous acceleration, which is a Bloch type oscillations. And in our case, we improved this Bragg sequence by using a coherent phenomena to make the losses to interfere destructively. So, and then I will show you that we can use the floquet formalism to unify all these techniques and also to reach an optimal solution for the momentum transfer. So let's start with an example, and let's consider a sequence of Bragg pulse. So we can transfer momentum by 2 photon transitions with a sequence of 2 photon transitions. So for that, you need pulse. Each pulse transfer two H bar K, and for each pulse you have to adapt the resonance of these two photon transitions. So you end up with a sequence of pulses and a stepwise function for the Bragg conditions. Most of the experiments using this Bragg sequence try to optimize very well this single pulse in order to have a single momentum state which is diffracted. And to do that, you need to be in the adiabatic regime where you don't want to populate the nearby momentum state around a wanted transition. In our case, we did the exact opposite. And so we used very short pulse to have the losses dominated by the non-adiabatic losses, which are coherent losses. If now you use a vanishing time in between each pulse, you can have a separation between the different paths of the losses, which are smaller than the coherence length of your wave packets. And if you look at that carefully, you can show that each loss channel can interfere destructively. And so in this way, we obtain a very efficient pulse-to-pulse efficiency, which is about 99%. So the data are the circle here, and the line is a numerical simulation. Here we compare that data with the independent pulse model. So if you look at that, you have a limitation. First, on the age of the sequence, you have a pretty poor efficiency. So you need to solve this problem here. But if you want to close the interferometer at some point, you are also sensitive to the same efficiency here. So even if you have a very good efficiency, pulse-to-pulse efficiency, you still have this problem on the edge of the sequence. In addition, I told you that we wanted an efficiency which is much better than 99%. We want 99.9 something percent. So the question that we wanted to study is to have a higher efficiency, and also we would like to speed up again this momentum transfer. In our case here, we used in that experiment, we used a 40 microseconds pulse. So to do that, a convenient way is to look this scheme in the accelerated frame. So in the accelerated frame, the stepwise function in the accelerated frame, of the optical lattice. So if you go in this frame, so which correspond to the subtraction of a linear slope here, you end up with a phase of the lattice which follow a sawtooth function, which is also periodic, which is periodic. So you end up with an Hamiltonian which is perfectly periodic, and a very nice way to study these dynamical systems is to use the floquet formalism. So this is what we did. So a few words about it, but very short words about it. So the floquet theorem will tell you that you can calculate the dynamics of your sequence just by knowing what happens, the propagation over a single period or a single pulse, if we keep that image of pulses. So if you propagate the wave function through the pulse, you end up with a propagator. And if you diagonalize this propagator, you can find the eigenstate, which are the floquet states. So by definition, if you can prepare a floquet state, Wn here, you end up after your pulse with the same floquet state up to a global phase factor. So when you do that, you're happy because now if you start with a state Wn, after the pulse, you're still in the state Wn. So this is the new input state. And after the second pulse, you will be in the same Wn and so on and so forth. So you can stabilize your wave function in the Wn state, in this floquet state. In the accelerated frame, which means that in the lab frame, you accelerate your wave function. So with that, we were happy because now we have a clear solution, mathematical solution for what is an optimal transported state. Okay, so to be more clear on that, the floquet state does not depend on this. The fact that you have a floquet state, it does not depend on the specific shape of the sequence. Okay, for any kind of periodic sequence, you have a floquet state. So I've taken this Bragg sequence, but you could also imagine to have these square pulses, which are all put side by side. So you have a constant amplitude for your lattice and a linear evolution of the frequency. And so in the accelerated frame, you have a constant phase, so a constant frequency. So this is also periodic. So actually, you can, for any periodic driving of your lattice, you can find a floquet state. If we take a few examples, for the very deep Bragg regime, the floquet state will be a momentum state. For an adiabatic acceleration, the floquet state would be this Bloch state. And in our case, we are in some intermediate regime. And so our floquet state is determined numerically by a diagonalization of the propagator U. So here, this is our favorite pulse, which is a square pulse, a pi pulse, with a time pi, with a duration, sorry, of about 5 microseconds. So you see that it looks like that for the amplitude. This is a projection on the momentum state. And you have also this phase, which is different from the Bloch state that you might be used to see. So now we have a definition of this floquet state. The question that you could ask is, how can you prepare that state? Indeed, we start our experiment with a BEC, which is very close to a pure momentum state. So we have to accommodate at some point the P0 state or initial state with the floquet state. So a first solution would be to design the proper shape of your pulse to have a floquet state which corresponds exactly to the initial momentum state. So we did that. It works very well. And for a given time, it is very different from what we use usually, the Gaussian pulse that we use usually. But we find even more efficient by using a state engineering techniques. In that techniques, you take your sequence, your acceleration sequence, the best that you have, or your preferred one, and then you try to, so it corresponds to a W state, and then you try to add, well, not you try, you add a step here to transform the initial state to this floquet state. Then it is transported, and at the end of the sequence, you transform back the floquet state to the momentum state, or to a momentum state. So to find what happens here, this state-to-state, transfer is a well-known problem in the community of optimal control theory. So we ask them. So them are Dominique Souni and Etienne Dionis. They work in University of Dijon. So in practice, we have to control the amplitude of the lattice and the frequency of the lattice. So this is, as an experimentalist, I can play with these two buttons, or my student can play with that buttons. And then we need to find this best scheme for omega and omega, the amplitude and the frequency, that will maximize the figure of merit, which is our propagated state to the floquet state, to a floquet state. For that, they implement their recipe from the quantum optimal control, and in particular, they use the grape algorithm as well that we have heard just in the previous talk. So you end up with this kind of sequence. So for the experimentalist in the room, it's not that difficult. You don't have a crazy high frequency. Here, the scale is 100 microseconds for the amplitude, and here, this is the frequency. So now I have an animation, a movie to illustrate that. So it's not as fancy as a gravitational wave, but this is what I have. And okay, let's start. So here we start with the BC, P0. Then I use this OC, this control to prepare this W state. So here in the accelerated frame, it looks like that. And then it is accelerated. So in this accelerated frame, the floquet state is still the same. Why? In the lab frame, you have accelerated the wave function. And then you use again this optimal control step to transform this floquet state back to the momentum state, which is the state which propagates well in a free fall. And now I will explain you how we have implemented that experimentally. So we use a BEC. We have 30,000 atoms at 30 nanokelvin. And we manipulate the atom with a vertical optical lattice. We can control the amplitude and the frequency of the optical lattice using acousto-optical modulators. And we measure the momentum distribution after free fall. So here you have a typical data that we have for that kind of measurements. So we try to make exactly what I've explained, and we found that we have a significant improvement compared to the previous coherent enhanced Bragg sequence I spoke as well. But it is not as good as what we would expect. We would expect to have 100%. Okay, if you want to claim that you have an optimal solution, you want at least more than 90%. So the issue here is that actually for each momentum state, you have a different floquet state. So maybe I'm a liar, but I told you that the BEC was a perfect momentum state, but actually it's not true. The BEC is a distribution of momentum. So we have to find a simultaneous control to prepare for each P0 the correct floquet state. And it's not trivial at all, because you have only two controls: the amplitude and the frequency of the lattice, and you have to prepare an infinite number of states. So so this is what in the community of optimal control they call that robust against something, and here we want to have a protocol which is robust against P0. So for that they tried a new figure of merit which integrate all the momentum state. And actually on this simulation, you can see that for a quite wide or a quite broad distribution between 0.6 and minus 0.6 h bar k, you have a perfect preparation of the floquet state. So we have implemented that on the experiment, and we found for the same temperature something which is almost perfect. So for this acceleration, which is 20 h bar k, we have almost a perfect acceleration, and we verify by changing the temperature that we are still robust over a large range of temperature, and actually we have shown that we can be quite robust over a 0.5 h-bar-k, which is typically what people can use in a metrology, in experiment of metrology with a velocity selection of your source. So then we wanted to, we tried to find the limit of this technique. So I show the remaining fraction after an acceleration and a deceleration. So we have to do both to be sure that we stay in the detection volume of the experiment. So at the end, we managed to implement 1,200 h-bar-k as a total momentum transfer with more than 50% of the atom accelerated. So that corresponds to an efficiency per h-bar-k of 99.95% efficiency. The pulse lasts for have a duration of 5 microseconds, which corresponds to a rate of 2.5 microseconds per h-bar-k. So we have, so this is to my knowledge something which is at the state-of-the-art level. And for the efficiency, I think that's the best value, but you can tell me if I'm not aware about the biblio. We have identified two limitations: the spontaneous emissions and the fluctuation of the lattice. So regarding the spontaneous emission, we could increase the detuning compared to the excited states, as this is achievable with the laser system that exists in other labs. And for the pulse-to-pulse fluctuation, so here to have that limit, we implemented a 4% amplitude fluctuation. So, but it could be also due to phase fluctuation. We are still investigating that limit. So we have a nice acceleration, and then we try to implement that technique into an interferometer. So for that, you accelerate, then you decelerate one arm, and you do the symmetric acceleration and deceleration on the other arms. And this is this way that you do the LMT interferometer. So we have to face a problem here, is that our floquet state are quite broad. They are distributed over many momentum states. So at the beginning of the separation here, you can have a floquet state that could be that could mix with the other arms, and so this is not what you want. You want to have two distinct arms. You want to address the two arms separately. So for that, we have implemented a pre-acceleration with our Bragg with longer pulse, which can address only a single momentum state. And when we have a separation of 20 h-bar-k, we applied our floquet accelerations. And we do the same for the decelerations and the symmetric. We do that on the symmetric way on the other arms. So now we can, you have the geometry of our interferometer, and now the point is, how can you scan the phase of your interferometer? And even more importantly, how can you be sure that the fringes are correspond to the main interferometer and not to a parasitic interferometer, okay? Because you can have many atoms with only a few percent into a parasitic interferometer. So for that, we apply a phase jump onto the laser pulse here, and this phase is imprinted onto the atomic phase, as you know, and depending on how many pulses see this phase jump, that will change the period of the fringes. So in particular, if you apply this phase jump onto all the accelerated pulse, you will have a phase which scale with NF times this phase jump. So we did that. for an interferometer of 600 H-bar-K. This is typically the maximum momentum transfers that we can achieve in our experiment. So if we do more, we don't see the atom anymore in the detection volume. So it is the limit here is not due to the fact that we don't have contrast anymore. It is just due to the size of the experiment, if you like. And so there's no fundamental limit for that number. We have a velocity visibility of 18%, corresponding to that. So in that case, the oscillation corresponds to the maximum period. So it is when k is equal to nf, and then we change k, and we found that the velocity is similar to this number. So we think that this 18% is limited by spontaneous emission. We also evaluate that the pre-acceleration here is not as efficient as the floquet accelerations, and that limits also the visibility. Now we are also convinced that due to the fact that you have this, I told you that we have a floquet state up to a global phase factor, but this global phase factor depends on the intensity. And so if the intensity is not homogeneous, so you can have a dephasing when you integrate all your ensemble. But this is clearly under investigation, and I will tell you more when we have the answer on that. So now I'm coming to the end of my talk. So I've shown you that with the floquet formalism, you can describe very well an acceleration from Bragg diffraction to the Bloch oscillations. I've also shown you, I try to convince you that it is a very efficient way to implement optimal control for a large Hilbert space. If you try to find, if you ask to your algorithm to optimize from 0 up to 100 H-bar-K, for sure it doesn't work. So we tried very strongly, but we never succeeded, even with people very, very skilled on that things. And the most important result for me is that we achieved a 600 H-bar-K interferometer, and I think we can get a greater, with that techniques, we can achieve interferometer with a momentum transfer greater than 1000 H-bar-K. So for that, we need a few improvements. First, we plan to use this quantum optimal control to design this beam splitter pulse to directly converge to the situation where we can accelerate. You can use this floquet accelerations. We are also studying the question of the lattice depth fluctuation, which is quite a big problem in the community of LMT interferometer. So you have a problem of what kind of systematics of phase of diffraction phase you can have using that kind of technique. So we try to see if we can find some to engineer some pulse to mitigate this effect. And finally, we have some discussion and some experiment to study the how we can apply that technique to metrology for metrological experiments. So I have finished my talk, and so I want to thank a lot this team. So this is Baptiste, which is my colleague, also professor in the group, and Ashley and Tanguy was a former PhD student, which worked a lot on that experiment, and Célian and Leo work also on that experiment. Clara is a new student on the LMT, and I hope she will solve all our problem. So thank you.
Great results. So in the double Bragg diffraction and the corresponding Bloch oscillations, the line field distortion had been somehow simulated to be a significant problem. So how is it in your method?
I'm not totally sure about the distortion of the
laser beam. You have the light beam.
Okay. So your question is if I have a floquet state which depend on the intensity, light intensity, if the intensity is not the same everywhere on the cloud, you can have dephasing. So we tried two things. First, we tried to find another figure of merit in the quantum control to limit this this effect, to be robust against this amplitude fluctuations, a static modification. So here you see let me think. The dotted one is the experiment and the blue one is what you would obtain with a better cost function. So you can try to no, it's not the proper curve. Sorry. Oh, this is this one. So you can try to, if you decrease a little bit the efficiency of your sequence, you can improve the sensitivity to the phase shift, the dephasing due to that effect. This is for the sensitivity to the Bloch, not the Bloch, the floquet state. And then another advantage of the floquet state that you can use it to make some analytical calculation. And we have shown that from perturbation theory that using this floquet state, that at some point you have some phase that depends on the time that you spend into the laser. And this is intrinsic to the dynamics. I think you cannot really improve that a lot. I think okay, in the experimental, in the data I've shown you, I think the visibility from rough calculation is limited by this effect at most at 60% of the visibility of 60%. But okay, I need a proper theoreticians to do that.
Quick question, great results, and thanks a lot. I don't know if my eyes are tricking me, but for the 17–18%, could vibration-induced phase noise also play a role and give you a few more percent? So when you go back to the fringe, it seems like maybe the fit could give you slightly larger amplitude. Did you look into vibrations?
Okay, yeah, I can answer that. So okay, in the Uzimi representation, your floquet state look like that. Okay, and so you could imagine, obviously, that if you have vibration, the phase is not the same for each pulse, and so you lose the periodicity. But that would correspond to a displacement, an acceleration, if you like, that you have to compare to that displacement, which is related to the main acceleration, which is 200 g. So, and the width of this state is about is in unit of acceleration is about the same. So you need a very, very strong acceleration to decrease a lot the efficiency. You mean on the interferometer, not on the sequence? Okay, okay. Yeah, but well, we've made some measurements with a seismometers, And if we try to see what kind of phase noise we would have with the areas that we have here, it shouldn't be, it shouldn't explain this 20% contrast. I'm not telling you that when we will have 70%, it is not. Well, another way to say is that here we don't have that big area. We do everything in few milliseconds.
Okay, very good. I guess everybody is ready for dinner. And let's thank Alex and all speakers of this beautiful session. Any announcements? Well, poster session.
Just a reminder, poster session at 8, outside there. And the steering committee and program committee, please stay here for one moment.